Let us now try to understand degrees of freedom and internal actions. A point in a three-dimensional space defined by Cartesian coordinate system has 6 degrees of freedom. These degrees of freedom include 3 translations, each along respective axis, and 3 rotations, each about respective axis. Let us now assume that a structural member is aligned along x-axis. When referring to a point on a cross-section of that structural member, we can relate each degree of freedom to corresponding internal action. The translation along x-axis can be related to axial force. The translation along y-axis can be related to shear force in y direction. The translation along z-axis can be related to shear force along z direction. The rotation about x-axis can be related to torsion. The rotation about y-axis can be related to bending moment about y-axis, and the rotation about z-axis can be related to bending moment about z-axis. Continuing our example where our structural member is aligned along x-axis, we can now represent each internal action based on the corresponding axis about which it is defined. For example, we can define Vx as axial force that's of compression or tension in nature, Vy as shear force in the direction of y-axis, and Vz as shear force in the direction of z-axis. In the rotations group, we have Mx, which is moment about x-axis, which is known as torsion or twisting. Then we have My, which is bending moment about y-axis, which can be viewed in xz plane, and Mz as bending moment about z-axis, which can be viewed in xy plane. If we reduce the three-dimensional problem to two-dimensional problem, which generally is the case when we analyze beams and columns and frames, depending on the geometry, we can eliminate some of the internal actions. For examples, for geometries in xy plane, we can eliminate 3 internal actions. The important internal actions for the geometries in xy plane are Vx, Vy, and Mz. Notice here that for the geometries lying in a plane, the rotation component is always defined about the axis perpendicular to the plane of the geometry. For example, over here you can see that the geometry is in xy plane. So the bending moment is defined about the axis perpendicular to that. Axis perpendicular to the xy plane is z. So the rotation component is defined about the z-axis. Similarly, if the geometry is in yz plane, the rotation component is about the x-axis. And the force components are Vy and Vz. Similarly, for the geometry in xz plane, the rotation is defined about the y-axis, which is an axis perpendicular to xz plane.